In this video, we are going to learn how to do problems where a car rounds a curve. This is a certain type of circular motion problem. So for sample problem 1, we're just going to have a horizontal surface. So a 2,300 kilogram car rounds a curve of radius 20 meters. The coefficient of static friction between the tires and the road is 0.23. The roadway is horizontal. What is the maximum speed the car can have? So there's a car rounding a curve. Remember that the centripetal force always points towards the center of the circle. So let's go ahead and draw in some forces. So this force of static friction, which is what's causing the centripetal force, points towards the center of the circle. And the force of static friction acts as the centripetal force because it allows the car's tires to stay in place around the curve. The radius is 20 meters. And why is it important that the roadway is horizontal? Well, that's so that we know the normal force is equal to the weight of the vehicle. So we know that the formula for the centripetal force is Fc equals mv squared over r. And we know that it's the force of static friction that's causing that centripetal force. So Fs equals mv squared over r. And we know that the formula for the force of static friction is the coefficient times the normal force. And again, since the roadway is horizontal, we know that the normal force is equal to the weight. So we can replace this Fn with an mg. Now, notice at this point that the m's cancel out. So I didn't even need to give you the mass of the car. And we can start plugging in numbers at this point. So I want to plug in 0.23 here and 9.8 here. I'm looking for the maximum speed that the car can have, and then I want to plug in 20 for r. So 0.23 times 9.8 and then times 20 is 45.08. Then take the square root of both sides, and you get that the speed is 6.71 meters per second. That's about 15 miles per hour. So what would happen if this car goes faster than that? Well, this force of static friction wouldn't be enough to hold the car in place around that curve at that speed, and the car would spin out and go off the road, which is not good. So knowing how tight the curve is partially how they come up with those speed limits when you see them on roads. When you go around a curve, it's those yellow signs. They'll look at how tight the curve is, and then they'll come up with a speed limit based on actual physics problem solving. Now, you should have noticed that we canceled out the m's here. What that means is that the mass of the vehicle doesn't matter. So it doesn't matter if it is a truck or a car or a motorcycle. The vehicle should not exceed this speed right here. Now, from a physics perspective, let's think about why the mass doesn't matter. Well, it seems like it should matter because the more mass, the more force you would need to hold it in place. However, you also have to keep in mind that the more mass an object has, the more the force of friction is acting on it. So it needs more force, but it also has more force available. So hopefully that makes some sense. It needs more force, but also has more force in the first place. Okay, sample problem number 2. You may have seen banked curves when you're exiting highways or going onto highways. A civil engineer wishes to design a curved exit ramp for a highway in such a way that the car will not have to rely on friction to round the curve without skidding. Suppose the designated speed for the ramp is to be 48 kilometers per hour, and the radius of the curve is 50 meters. At what angle should the curve be banked? So let's start by visualizing this. So we've got this car on the banked curve. You kind of have to imagine the car going around in a circle. It's going into the PowerPoint presentation right now, or into the screen. So let's draw some forces that are acting on this car. So we've got the normal force acting perpendicular to the curve or the banked curve. We've got the force of gravity or the weight going down. I'm going to call the angle of the bank theta. And remember that the centripetal force always points towards the center of the circle. So I've added some things in this drawing. I specifically drew the centripetal force pointing this way because that's the center of the circle. And then we also know that the normal force is going to have an x component, which I've drawn up here, and a y component, which I've drawn here. So I'm going to take this bit that I have right here, kind of zoom in on it so we can analyze the components of the forces a little bit easier. So we've got this set up. And this arrow right here is just Fn, but pointed in the opposite direction. We know that this angle right here is 90 minus theta, which would make this angle equal to theta, which would also make this angle equal to theta. Now the reason I'm doing that is because I want to write Fnx and Fny in terms of Fn. So what would happen if I took the cosine of the angle? Well, cosine is adjacent over hypotenuse, so the cosine of the angle would be Fny over Fn. If I rearrange that for Fny, I get that the y component of the normal force is equal to Fn cosine theta. If I take the sine of theta, I will get Fnx over Fn. If I rearrange that for Fnx, I will get that Fnx equals Fn sine theta. So we're used to having the x direction be cosine and the y direction be sine, but notice that that's not the case here because we're looking at this problem differently. You might also be wondering, hey, don't we already know the normal force? Shouldn't the normal force on an inclined plane just be equal to mg cosine theta? Well, that's not the case here because this car is moving. So it's staying in this circular path. So the normal force is actually going to have to be bigger than it is in a regular sort of inclined plane problem. We'll get back to that in a little bit. So I'm going to transfer this to the next page. So we know Fny and we know Fnx. Now, this car, represented by this dot, is not moving up or down, so all of the forces in the y direction need to cancel. And what that means here is that Fg has to be equal to Fny. And Fg is equal to mg, so Fny equals mg. And now we have to think about, where does the centripetal force come into play? What is actually providing the centripetal force? And the answer is that it's the x component of the normal force. So Fnx equals Fc, and we know that Fc equals mv squared over r, so Fnx equals mv squared over r. Now our goal here is to find theta, so we don't really have theta. Like basically we just have this massive system of equations right now. So we want to narrow it down so we can actually solve for theta. So I know that Fny is equal to Fn cosine theta and Fnx is equal to Fn sine theta. So I'm going to go ahead and plug those in. So basically this is really similar from just working with vectors. So this is my equation for the y direction and this is my equation for the x direction. So now I have a pretty simple system of equations. And again, remember our goal is to solve for theta. So what I'm noticing first is that I can take this equation, solve for Fn, and then plug it into the x equation. So the normal force, Fn, equals mg over cosine theta. I'm going to go ahead and plug that in right there. So I get mg over cosine theta times sine theta equals mv squared over r. So this should start looking a lot better at this point. So first, I didn't give you a mass on this problem, and at this point we should see that the mass just cancels out. Also, you should see that sine over cosine, that's a trig identity. Sine over cosine is equal to tangent. And we can also plug in numbers. So G is 9.8. V is 13.34, and R is 50, so that's what I've written over here. And then we can just solve this expression that I have here for theta. So 13.34 squared divided by 50, and then times 9.8 is 0.363. And then theta is equal to 9.96 degrees. So this has to have about a 20-degree angle in order for the car to be going at that speed around that curve. Now, let's address this. Why is the normal force not equal to mg cosine theta? So in fact, we have that the normal force is equal to mg over cosine theta. So the normal force in this case is actually larger than the weight of the object. So why is that? Well, that is the case because this normal force has to be doing more things than just preventing the car from, going through the surface or going through the roadway and braking it. So the normal force has to be holding the car against the full weight of gravity, and the normal force has to be holding the car in place around that curve. So that's why it has to be bigger than the weight of the object, because that force is doing multiple things at once. Also notice that the mass ends up not mattering here. So let's think about why that is. Well, it's the normal force that provides the centripetal force for the vehicle. So if the vehicle has more mass, it needs more of a centripetal force to hold it in place, but it also inherently has that greater centripetal force because it has a greater mass. So hopefully you understand how to solve car rounding a curve problems now.